Today we will quickly go through the previous lecture because some of the students have hard time to obtain the closed loop system for the second system. So the original question is given these two systems, okay, using stepping approaches, and we expect you to do the control, to do a tracking control for x1 to track x1d in the system where ABC are unknown constants. So you need to use backstepping and adaptive approach to design the controllers. So this is for the first system. We define the tracking error E, which is the mismatch between x1 and the desired trajectory x1d. Okay, so here is fine. And in this system, we introduce y1 and theta 1, where theta 1 involves every unknown parameters a and b plus c. So I think I had a typo here where it should be y1 and theta 1, and before I had y and theta, so change y and theta to y1 theta 1 because I have y2 theta 2 later in the second system. So you just put unknown parameters, which is this, into theta 1 and y1 regression. So here should be fine, the virtual control input, and the closed loop error system for the first system. So the second system is more challenging because you have more unknown parameters introduced into the system. So x2d is the virtual control input for the previous system, the system 1. Here, your control input need to compensate not only this unknown term, but also this x2d dot term. So we take the time derivative on x2d here, which is the virtual control input of the previous system. And it's more complicated when you take the time derivative on all these four terms, because what is critical here is that when you take the time derivative here, you will see that you need to use it decomposed into two parts, right? First, you take the time derivative on the first part and then the second part. And especially in this y1 dot, because y1 is a function of x1 as well as function of time. Some of you might miss this term, okay? Some of you might just write y1 transpose equal to this term, but they forgot this term. And this term makes a little bit difference. Next, if we expand these terms, you will see that this part is from the time derivative of this. So by using this note and substitute the result into here, you can spin out y1 transpose and theta hat. And this part is just the time derivative of x1 squared and time derivative of x1d dot and k and this term. So next, what you need to do is regroupings. Okay, the difference between here is regroupings. I regroup the terms with x1 dot, which is this term, this term, this term, three terms into one bucket. Because x1 dot is from the open loop dynamics, which contains unknown variables. x1 dot contains unknown constants, a, b plus c, and some known constants. So it's a combination of unknown parameters and known functions. In here, I will regrouping the term with x1 dot, and the rest of the terms should be some known functions. It's known. Everything here is known. Unknown term might be included in here, okay, which is this. So I substitute x1 dot here and go to the next slide. You expand x1 dot, okay, and segregate the unknown terms and the known term into different brackets. You put the unknown terms a, b plus c, and a squared into theta 2, which is a new theta. Previously, we just had theta 1, okay, in the previous slide. Now we have theta 2. So theta 2 is this. You put all the unknown variables, and this is regression matrix. And omega is a known function. And we also introduce omega 2, which is a function of omega and some other known functions, and plus some terms. All this is a known functions. This is measurable. The takeaway is you regrouping terms into unknown terms, known terms. And for unknown terms, we just do adaptive control to take care of this part and compensate the known terms in the control input. Okay, so in your control, you will expect to see omega 2. In your control input, you will see omega 2 to cancel out another nonlinear omega 2. Okay, and this part is the adaptive terms. This is feedback term, cross terms. In the end, you will see the cross layout system for season 2 is this. In the debug function, because you have two theta 1 and theta 2, so you need to include that in your debug function. And substitute the cross layout system 1, season 2, and the adaptive load for theta 1, theta 2, which is this. You can show that beta will be negative semi-definite. And use Barbara's lemma to show that both error will converge to 0, which is globally asymptotically stable or tracking. This is the new version, which is version 3, is on the Google site. Okay, so a bunch of calculations, just calculation, but the logics, the analytic methodologies remains the same. Okay, how you regrouping terms, how you cancel out the nonlinear terms, cross terms, feedback terms. Material is same as previous year. Second midterm will not include this part because they will be too challenging for you guys with a closed loop test exam. But I would expect you to go back to review maybe after this class, after this semester, when you have some similar problems that you need to solve using the same tool as this section. You might be capable to recall what you have done in this course. Okay, so you can go back, open the note, and pick up all the concept in here. So you can reuse and have you to develop controllers in your future research work. So you have to understand the objective of this section. What's the problem and why we need to introduce these tools to deal with the problems. And what's the difference between this and what I have been covering in the previous lectures. So the objective for using DCAL, which stands for Design Compensation Adaptive Load. The reason to introduce this approach is from one perspective. It's an output feedback control for Euler-Lagrange systems. Okay, what is output feedback? Anyone heard about output feedback? Anyone heard about state feedback? What is output feedback? Zhongshan, what is output feedback? For example, in the robot manipulator case, if you have two-arm robot, here's your end effectors. You want to control the end effector to track some reference trajectory. Okay, so some desired trajectory. That's in the 3D space. Okay, this is in text space, right? Text space. And here you have is a two join robot, which is join 1, join 2, Q2, we say Q1. This is what you can control. But usually the sensor to measure the difference or the tracking error is a camera, right? Camera, they observe the difference between two, this is X and this is XD, okay, XD. So the tracking error is XD minus X. So it's observed by the camera, right? In your controller, you will design what feedback terms. usually feedback term, which is maybe minus KR. R is maybe E Q dot plus alpha Q. Be I, for example, right? To be simple. So what you can measure is the position error, right? But in the control, in your torque, apply on each joint, we call it torque, right? Which control the acceleration of the joint. In the feedback term, we will design feedback term, maybe cross term, whatever terms. This term, which is R, it requires the input of Q dot, velocity terms, or some Q, maybe E dot terms, the E dot, the velocity of the tracking air, because you are control the acceleration. And it's better have both position and velocity error. But what your sensor can measure is position error, not the velocity error. In other words, your state could be position, but your sensor or measurement only measure the position. But in your control, you require both position and velocity error. What you know is only the position error. So you cannot use sensor information to do control. Okay, you need to somehow estimate not only position but also velocity. In the linear system, usually we have this equation which says that Y is the output, and this is the state. Okay, so if C is 1, 0, 0, X is your state, C is the measurement matrix. So if in this case, you can only measure a position, right? So this measurement matrix will be 1, 0, 0, which means you can, this output is only position. Okay, you cannot measure state. The velocity term is required for control. So that's the motivation for DCAL-based control. Okay, it's an output feedback. It's not state feedback. Here we call it output feedback. We only use sensor information, the measurement information for feedback. We don't use the full state. Here only Q and E are measurable. Okay, the angle and the air are measurable. So only Q is measurable, not Q dot, not Q double dot. Okay, only Q is measurable. And of course, your desired trajectory have to be bounded. QD, which is desired trajectory, have to be bounded. So given the same order Lagrange systems, which is M, Q double dot, and Vn, G, and F, Q dot equal to tau. Here are some properties. M is positive definite because M is the inertial matrix, right? Or the minima value for any inertia or any mass will be greater or equal to 0. So you have to be positive definite matrix for M. And it's skew symmetric, which we have talked about this before. Switching property, you can switch Vm times C, where Vm is a function of A and B. You can swap the variable A and B with the C. Okay, you can swap B and swap C. Swap, exchange. 把 C 放里面 B 放外面就变右边了。Only the second variable in Vm. And Vm has some bound. Vm can be upper bounded by some constant times the Q dot norm. Again, the second variable. It can be bounded by some constant times the norm of the second variable. And here are some bounds. So the approach is we define a P filter. P filter, here we call the P filter is here, the P. P is the filter, and it follows this dynamics. Okay, P dot equal to all these equations. So this equation is called P filter. P, you can consider P to be like acceleration terms, because acceleration is not measurable. So we design a signal to mimic the acceleration. You can check out here that for to implement this filter, what you need is only the E signal, the tracking error. And tracking error is only a function of your desired trajectory and your current position. So it doesn't contradict with the assumption where only Q is measurable. 只有 Q 是可以量测的嘛，所以当你 implement 这个 filter 的时候 ，you can only use Q, but not Q dot, Q double dot. Okay, and E is a function of Q. E is the tracking error. And we also define R signal. Okay, it's different from the filter tracking error. The R defined here is E dot plus E plus EF. And EF is a signal defined as this. It's a function of P filter, P here. So you can see here that EF is an auxiliary signal motivated by the output feedback control, output feedback, okay? And P is the feed filter. These three equations need to be calculated together because R depend on EF, EF depend on P, P depend on E, and what will be used is EF and P. Let's do the analysis. So given the R signal defined here, and we take the time derivative and multiply M is equal to this based on the definition of R. So you substitute for E dot equals to QD double dot minus MQ double dot. Okay, so this part is MQ double dot. E dot is equal to, according to this, is equal to R minus E and EF. R minus E and EF. Okay, and for M, EF dot is equal to, you take the time derivative on this, so you have minus KE dot plus P dot. So minus KE dot plus P dot. And this part is equal to 0 because you add and subtract YD theta. Next, we focus on this term because remember we say Q dot is not measurable. So we need to decompose Q dot to a different form. We need to replace Q dot to be a function of measurable terms, which is the tracking error and etc. So we replace Q dot to this using the definition for tracking error E, and we replace E dot by this based on the P filtering. Okay, based on this. Then all these signals are now measurable. This equation, the first equation now can be rewritten in this form. So we just spend all these terms, substitute the open loop dynamics, substitute the P filters, okay? And this is add and subtract the same terms. What is the regression matrix along the desired trajectory, the XD, okay, theta is the unknown parameters. So that's because this term is not measurable, right? From the assumption Q is measurable because it's output feedback. You can only measure Q, but Q double dot are not measurable. It's not measurable. So replace Vn Q dot. So Q and Q dot is a function of Vn. Okay, we replace Q dot. We replace this by QD dot minus E dot. The tracking error. And because E dot is still contains the non-measurable term Q dot, right? So we replace E dot by R minus E and EF. Because all this R, EF, P is measurable. It's the filter you design, so every signal in the filter is measurable. So we replace the non-measurable term by measurable terms. The first equation can be rewritten as this. And now your MR dots becomes, so we assume that the open loop dynamics, which is this, right? And we assume that theta is the unknown parameter, right? And YD stands for, you substitute, is the regression matrix along the desired trajectory, because Y is a regression matrix which is a function of Q dot and Q double dot. But if you replace Q by QD, which means along the desired trajectories, then you can replace every argument Q by QD, okay? QD, 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 QD. So it's equal because we try to approximate these dynamics along QD, along the desired trajectories, okay? Okay, we put this term next to this term. Okay, we combine this term together, which is this. That's what I'm doing here. Okay, you break MQD, QD double dot, and every QD terms, because YD theta have 4 terms which replace Q by QD. So this is the first term, second term, third term, and the last term is here. Okay, and for the rest just remains the same. 这样看得到吗？黑板不够大。The board is not large enough to let me put all the equation on the board. So using this equation, okay, and substitute back to here, and using that relation, using this relation and that VM back and substitute back to the first equation, you can get this. Here are more to come, so maybe next time. So eventually it's semi-global tracking. For example, the difference of these two terms can be upper bounded by tracking errors. Okay, that's why I decompose this and put this term together. So the rest of the work is just regroupings, substitute, reuse all these equations, regroupings, upper bound by error norms, and that's it. Okay.